Converging lenses. A thin lens is a lens whose thickness is small compared to its radius of curvature. Lenses can be converging or diverging. Converging lenses are thicker in the center than at the edges. Diverging lenses are thicker at the edges than in the center. Converging lenses bring parallel rays to a focus, which is the focal point. Diverging lenses make parallel light rays diverge. The focal point is the point where the rays would converge if they were projected backwards. For plane mirrors, images are always virtual and they're always behind the mirror. This is because image formation in a plane mirror is based on light reflection. For lenses, images are real if they're on the opposite side of the lens from the object. They're virtual if they're on the same side. This is because image formation is based on light refraction. Ray tracing can be used to find the location and size of the image created by thin lenses as well as mirrors. These are the steps for converging lenses. For the purpose of ray tracing, label a focal point on both sides of the lenses. The first ray enters parallel to the principal axis and exits through the focal point on the other side of the lens. The next ray enters through the focal point on the same side of the lens and exits parallel to the principal axis. The last ray is my favorite. It goes straight through the center of the lens and is not deflected. Once again, unlike mirrors, lens images are real if they're on the opposite side of the lens from the object. The images are virtual if they are on the same side as the object. So virtual images will be over here. Real images will be over here. The image created by a converging lens will be examined for 3 different object positions: outside the center of curvature, between the center of curvature and focal point, and within the focal point. An object, typically represented by an arrow, is placed outside the center of curvature, here. Draw 3 rays to find the image. The first ray goes parallel to the principal axis and then exits through the focal point on the other side. The second ray enters through the focal point on the same side as the object and then exits parallel to the principal axis. So we already know where our image is going to be, but let's do the third ray. The third ray, which isn't necessary, but is nice to confirm you did the other ones correctly, goes straight through the center of the lens and is not refracted. And then here, at the point where they all intersect, we start at the axis and we draw our arrow to the point of intersection. The image, as you can see, is smaller, so it's demagnified. It's real because it's on the other side of the lens, which means it could be projected onto a piece of paper or a screen. And it's upside down, so it's inverted. Let's look more closely at what that means. The arrows indicating the object in the image are copied out of the ray diagram here in order to illustrate what it means to be demagnified. Compare the size of the 2 arrows. The image of the object is smaller than the actual object, therefore it is demagnified. The arrows indicating the object and the image are copied out of the ray diagram to illustrate what it means to be a real image. Compare the location of the 2 arrows. The image of the object is to the right of the lens, so it is a real image. The arrows indicating the object in the image are copied out of the ray diagram to illustrate what it means to be an inverted image. The image of the object is upside down. You can see that the image arrow is pointing down while the object arrow is pointing up, compared to the actual object. Therefore, the image is inverted. It's upside down. Now we move the object in between the focal point and the center of curvature. First ray goes parallel, then through the focal point. The second ray enters through the focal point on the same side of the object and then exits parallel to the axis. So we already know where our image is going to be. Let's confirm it with our third ray.
The third ray goes through the center of the lens and is not refracted at all. We only need 2 rays to see where the image is located, but 3 or more rays will confirm the location. The image is magnified, real, and inverted. All right, now we have moved the object between the lens and the focal point. The first ray goes parallel and then through the focal point. The second ray is a bit tricky. It's going to start at the focal point, touch the top of the arrow, and then the lens. This is very similar to when we were inside the focal point with a concave mirror. Then it's going to go parallel. So you can see these 2 rays are not going to converge on the right side of this lens. The third ray starts at the top of the object, goes right through the center of the lens. These rays do not intersect on the right side of the lens, so a real image is not formed. When that happens, we're going to dash back the lines. We extend them backwards, where they will converge, here, on the same side of the lens as the object. Therefore, this is a virtual image. It is also magnified and upright. Here is a summary of all of the image formation information for a converging lens based on object position. A candle is located 22 centimeters away from a converging lens that has a focal length of 10 centimeters. Draw a ray diagram and describe the image formed in terms of real or virtual, its location and magnification. All right, so we draw our object back here. See how this is going to be 10 centimeters is the focal length. C, the center of curvature, is always twice the focal length. But our candle is located 22 centimeters away from the lens, which means it's a little bit out here. It's beyond the center of curvature. We draw a ray diagram, and you can see that the image is smaller, so it's demagnified. It's on the other side of the lens, so it's real, and it's upside down, so it's inverted.